Good day. This is our start to the chapter 16 on solutions. Some of these things you'll recall from earlier chapters, and a lot of it should be new. So you should know first of all that solutions are mixtures, but they're so well mixed they look the same throughout, and that's why they're homogeneous. They have a solvent, and they have at least one solute. So we're going to look at solutions in two ways. First, qualitatively, that means without numbers, no math involved per se. And people go, oh, that's going to be easy. And in fact, it's the harder section. So easy stuff will be dissociation. Solubility, precipitate formation, we'll look at that today as well. And you really have to get good at using a solubility chart. You have to get good at types of equations, formula equations you're used to, and then full or total ionic equations, and then net ionic equations. And then what many students find the most difficult is qualitative analysis. So some of these things will look like mumbo jumbo, but we will work our way through them. The quantitative turns out to be pretty straightforward. Yes, we have to be able to write dissociation equations to work out concentrations. That's easy. We can mix solutions with no reaction. That means no precipitate, and find concentrations. That'll take a bit of effort. And then the hardest we'll do is mixing solutions and finding ion concentrations or the mass of a precipitate. So in this case, by reaction, we mean we made a precipitate. So first of all, dissociation. If you dissociate from your friends, it means you move apart from your friends. So when a compound dissociates, we're talking about ionic, it splits into its ions as it dissolves. Ionic compound must be soluble in water for it to dissociate, and so we have to learn how to use a chart to figure out if things dissociate or not. And the subscripts become coefficients. Again, mumbo jumbo till we do examples. Now, there are 9 combinations that give us different types of solutions. So what we're saying is we can have our solvent be a solid, liquid, gas in all cases, and we can have our solute be a solid, a liquid, or a gas. So solid and solid means to get copper and zinc, you would have to heat them up to the point where they melt and stir them together and then cool them carefully to have an alloy. Solid and liquid, mercury and silver. So you can dissolve silver in mercury, and that's the way they used to make fillings, and that's why I have considerable brain damage. You can't use that excuse. I suspect they don't use mercury anymore. And hydrogen dissolved in platinum. So we have all these interesting combinations. There's antifreeze, soda pop. So when you have carbonic acid formed by carbon dioxide and water, you have made a solution, and that can be in pop or actually carry quite a few solutes in your blood. And then we have other ones there, and air, of course, is a mixture of gases. Let's look at dissociation equations. So KBr is going to split into K plus and Br minus. Dissociation equations, this is one of the most stickiest chapters. You have to put in the states for each chemical, and when they're ions, you have to put in the charge, and it has to be balanced. This is a one-to-one deal, so it's no problem. This is really the reverse of writing formulas. Instead of sticking things together, see now they combine, we're breaking them apart. So we know that this is going to split like this after the silver. And so we get a silver plus ion and a nitrate. Notice we have charges, and it's 1-to-1. And we go hi-ya, and it's going to split there. Now, this 2 says every time this breaks apart, we get 1 zinc ion, 2 plus, but we get 2 chloride ions. So that 2 became a coefficient. Now in this case, that 3 doesn't become a coefficient because nitrate, NO3, is a team. This one's pretty easy to know where it splits because we've got the brackets. So when this splits, we're going to have a PO43 minus, and we're going to have 3 NH4 pluses. We can't split up what's inside the brackets. So those are 4 examples of balanced dissociation equations, ionic compounds that are soluble, so it has to say AQ, splitting into its ions. Solubility is a measure of how well a substance dissolves. Now we're going to look at it qualitatively this year, and in Chemistry 12 we spend a lot of time dealing with the math of solubility, figuring out actually how much can dissolve in a given volume of a given material. You have to learn how to use the solubility chart. Soluble means it does not form or precipitate, and so we call it aqueous, symbolized by a little aq. Sometimes they'll be called low solubility or insoluble. For our purposes, low solubility and insoluble are going to mean the same thing, and that means the ionic compound that forms makes a precipitate. It doesn't dissolve, and therefore it's indicated by a lowercase s in brackets, solid, a little subscript. This is the chart that's going to be one of your best friends in this section. And we'll go through this chart, and then I'll stop the video, and then we'll do part 2 in the next one. So what we look at is if you have an alkali metal ion, so cations or positive ions, any of the alkali metals, doesn't matter what the non-metal is, it could be Br minus, it could be S2 minus, it could be a complex ion, they are always soluble. Hydrogen ion, same deal, doesn't matter what we have there, and the same for ammonium. So if you see any of those ions, you're going to say soluble, symbolized by AQ. But most of the time, we look at the non-metal to figure out what's going on, or I should say the negative ion. Nitrates are always soluble, doesn't matter what the positive ion is. Chloride, bromide, and iodide are usually soluble except with Ag+, Pb2+, and Cu1+. And Cu1+ is different than Cu2+. So Cu1+ would be low solubility, that's a solid. If we had Cu2+, it'd be up here, and it would be soluble. You can see with sulfates, only these 5 ions will precipitate out with it, making a solid. So it's soluble with most positive ions, just these 5. And with sulfide, we sort of flip, we go alkali ions. You got to remember, alkali ions include all of them. They list them here, but down here they just write alkali ions. So it's soluble with those, but most cations, it will be low solubility with. Hydroxide, very similar, only a few things are soluble. Most are low solubility. And these 3 ions behave the same way, and only a few things are soluble. Most are low solubility. So we're going to end this video right here. We're going to test how you understand the solubility chart when we start part 2.